All right, welcome back. So we've done the first part, which was free fall without air resistance. Okay, so free fall, no air resistance. And what happens? It's a tie. Objects are going to accelerate at the same rate. But now we're in part 2 here. What happens with air resistance? Okay, so, well, I'll tell you a story about the day that I went skydiving. I actually did go skydiving. It wasn't out of a helicopter, it was out of an airplane over by Gimli. I jumped out of a perfectly good aircraft in order to skydive. Let's analyze what happens as I fall. Okay, so diagram A is when I'm first dropping out of the aircraft. So I'm going to keep track of my velocity over here. So at this point, my velocity would be 0 meters per second, and later on I'm just going to make estimations of this. But now let's consider here what would be the net force acting on me. Well, looking at the free body diagram, there's a force of gravity downwards of 833 newtons, and there's nothing else. So the F net would be 833 newtons down. So, and the next question might be, well, what about acceleration? So acceleration is equal to F net divided by mass. So in this case, it's 833 divided by my mass is usually around 85. And so 833 divided by 85 is approximately 9.8 meters per second squared. And if the direction of the F net was down, then you know that the direction here of my acceleration is also going to be down. All right. Okay, so that's to begin with. So what does this mean if I'm accelerating? Well, if I'm accelerating, here I can just draw, that means that my dots are going to get farther apart. And I'm going to go faster. So a few seconds later, say, or maybe just a second or so later, let's say now I'm going 10 meters per second. Okay, so I'm going faster now. Because I'm going faster, that means now my air resistance has increased. I just want to point out this note I have up here. It says, note, the air resistance increases as the speed increases. If you've ever stuck your hand out of the window of your car, you know, you can feel the air resistance against your hand, and the faster your car is going, the faster the wind is going by, the more that force is. So as I get faster and faster, you're going to see this air resistance increase. So now let's consider the F net. Now that I'm moving along a little faster, my F net, well, I've got 833 down, I've got 350 up. So if I go and if I say, well, how much larger is that one? So if I subtract the two, I think I get 583. So I would get 583 newtons and downwards, because my down arrow is bigger than my up arrow. So the next question might be, if I fill in on the side here, what is my acceleration? My acceleration is F net over m. So now my net force is less because I've got this air resistance that's pulling up on it. And my mass, however, is still 85 kilograms. So when I divide this out, I get 6.8 meters per second squared. And again, these numbers are just kind of made up. But the point is, you're seeing the trend, aren't you? So to begin with, when there was no air resistance, 9.8 meters per second squared down. And if I have an object that air resistance is never really a factor because I'm not allowing it to ever get fast enough, or because its shape, that the air resistance is not a factor, then it's going to continue to be at 9.8 meters per second squared. But as soon as I get up to a significant speed and air resistance does occur, then you'll see how my acceleration is not 9.8, it's less than 9.8. Okay, so I was going 10 meters per second. Am I speeding up? I sure am. That's what this 6.8 meters per second squared down is. So that means a second later, maybe I won't go from 0 to 10, but I'll just make myself go up to 15 meters per second. So this is a moment or two later. So now I'm going to say, well, my F net is going to be equal to, well, how do these numbers compare now? I'm going faster, so my air resistance has gone from 350 to 700, 833 divided by, or subtract 700 is 133 newtons down. So my acceleration here is going to be equal to my F net of 133 divided by 85. And now my acceleration is a mere 1.56 meters per second squared downward. So I'm still going down and speeding up, but my rate at which I'm speeding up is much less. So if I pop over another interval of time, instead of going from 15, really a big jump, maybe I'm only going to go up to 17 meters per second. And again, I'm just kind of making up these numbers. So at this point, check out what happens. Now my air resistance, which has been gradually increasing because my speed's been increasing, now it gets to a point where my F net is, I think you're probably saying it out loud, my F net is 0 newtons. Well, this is a big moment. 0 newtons means that my acceleration is going to be equal to 0. I don't even have to do the math. 0 divided by 85 is still 0. So my acceleration is 0 meters per second squared down. We have some names for this. We can say constant velocity. Okay. We can say that in this case we have a special name. Call it terminal velocity. So terminal velocity means if you are allowing an object that's falling to speed up and speed up, the air resistance is going to increase until finally the air resistance is equal to the force of gravity, and they're not going to speed up anymore. Okay, so terminal velocity equals the maximum falling speed it occurs when the air resistance up is equal to the force of gravity down, right? And then, so therefore it's balanced, right? And balance means it's going at constant velocity. So that's how terminal velocity works, okay? So it's a bit more complicated, isn't it? Once we start putting air resistance in there, free fall with no air resistance, or if it's so small that we don't really care, everything accelerates at 9.8 and it's all the same. But as soon as we start talking about air resistance, it gets a bit more complicated, and things will keep speeding up, but they won't keep speeding up forever, because at some point it's going to be, the forces were going to be balanced. Well, what affects air resistance? And I think you know some of this. What if you're sticking your hand out the window? That old idea again. How fast that you're traveling through the air makes a big difference. So speed through the air. The faster you're falling through the air, the more air resistance, right? Also, the size or shape of the object. Okay, so if you stick your hand out and you put your hand kind of horizontal so that it's easy to cut through the air, it doesn't feel much. But if you put your palm towards the motion, you can really feel a lot of force, right? So how can you increase or change? Increase or decrease that air resistance? Well, change the speed, change the size, or shape. Okay, I've got a great little simulation here called Sim Bucket Skydiving. I just take a moment here. Perhaps we'll have some time to play it in class. So what happens here? Can I click on it and it'll play? All right. Ooh, it looks kind of funny. I think it's sideways on you. Maybe I'll stop it. Okay, I wasn't able to run that while doing this screen capture thing. I was doing funny things. So we'll do this in class, or take your time. You can do it at home if you've got a computer as well. SimBucket/skydiving TPC. Here, let's take a look. Here are 1, 2, 3, 4 objects, and they are all at terminal velocity. How can you tell that they're at terminal velocity? Because the air drag up is equal to the weight down, right? In all of these ones, here the air drag, the weight is 200 newtons, right? This is the same object all the time, and here it's 200 newtons all the time, okay? For these last three, what's different? Well, here is the block without a parachute. Here's another block with a small parachute, and here's a block with a large parachute. So what you can't tell by looking at my screen captures, my cut and paste of these three objects, is that this object, it didn't take very long, or I guess it says it took longer for this one, for the air drag to get that large, and at this point now it's moving downwards at 31.6 meters per second. This one has a small parachute. So by the time the air drag had increased so that it was equal to weight, and now it's falling at constant velocity, it's not going as fast, right? So if what we're doing from 1 to 2 to 3 is we're changing the shape. As we make shape or size, as we're adding a larger parachute on there, we're making the air drag larger, and so that the terminal velocity, here the terminal velocity is only 7.9, here the terminal velocity is 31.6. So if we're trying to answer the question, does a heavier object fall faster when air resistance is present? Well, here's a small object that's going at 10. Here's a big object, and it depends, or a heavier object, it depends on parachutes and shape and size. It could have a terminal velocity that's faster. It could have a terminal velocity that's slower. So really the answer on this question is it depends. Okay? Depends a lot on, I'd say, the shape, right? You could, for example, you could take a feather and a marble, and the feather is going to fall a lot slower than the marble. So what's the answer to what falls faster? Okay, it depends. Here's my back when summary is, if the speed is slow and F air is very slow, then it's like situation number 1. Then it's like free fall without air resistance. And then the all objects accelerate at negative 9.8 or 9.8 meters per second squared down. Okay, but the other version is if it is falling with air resistance, then usually the larger object will end up having a larger terminal velocity. Okay, so for example, you could say, let's compare a little speck of dust. Sometimes, like say, if you've got a lamp on and it's well lit, and you see just a tiny little speck of dust, and it'll be floating around, barely falling at all, versus maybe if you had a big clump of dust, a clump of dirt, right, that's much larger, and it would be falling faster, right? When speed is fast enough that air is significant, then that's its situation. Then we're falling with air resistance, and it's usually the larger object that will have the larger terminal velocity. Okay, so I hope that all made sense to you. You have a couple pages to work on in class, the air resistance and terminal velocity and skydiving pages, and we've got 2 sublevels for Newton's laws. I'll see you in class.